So now that we've finished the proof of the fundamental theorem, it's time to actually start computing Galois groups. So that's what we want to do today. And in fact, we'll probably do this for today, the next lecture, and possibly, I can't remember exactly how many examples I'm going to do, but 2 or 3 lectures worth of just examples of computing Galois groups. So that's what we're going to talk about now. So computing Galois groups. A little bit of lead-in. So what we're going to be interested in, so our interest, when we compute Galois groups, we're going to be computing Galois groups of polynomials. And so our interest is in the Galois group of F, which is going to be the Galois group, so gamma of sigma over k, where sigma is the splitting field of the separable polynomial f in k bracket x. In other words, right, our extensions are going to be Galois, which means that we're going to have a nicer flavor, I guess. So we can say then, gamma of f is Galois, and this gives us really a cleaner statement of the fundamental theorem, right? And the reason, right, so that if we look at the fixed field of the Galois group of k, so that phi gamma of k, in the case that our extension is Galois, we know that we have equality right here. Phi gamma k is equal to k. Right? And so, remember our script f that we is really our modified. Did I change that to tilde maybe? Oh, no, I'm calling it, I don't know, I feel like I changed it to tilde in the last lecture notes, but, oh, no, never mind. But so in that case then, script f is going to be the set of all fields that lie in between k and sigma, and script g is going to be the set of all subgroups of the Galois group of the polynomial, right? So it especially makes life easier right here. Instead of having a phi gamma of k, we just get k. So, so this gives a cleaner statement of the fundamental theorem of Galois theory. And so let's actually save this. I'm not going to put it as an alternate or a new statement of the, I'm not going to give it a new number, right? But it would go like this. So if sigma is the splitting field of the separable polynomial f in k bracket x, then gamma of f, gamma of f, sorry. So then we can state our 3 parts here. So part A, phi from script g hat to script F hat is a bijection with inverse little gamma. So remember, there's nothing to prove here. This is just rewriting it in the notation, right? Where, in the case that we have a Galois extension. So there's part A. Part B is that G is a normal subgroup of gamma of F if and only if the extension phi of G over K is normal. And then the last part, so if G is normal, or is a normal subgroup, then when we look at the quotient gamma of F mod little g, that's isomorphic to the Galois group of the extension, phi of G over K. And I want to say what this means now, especially part A. So, interpretation of A. All right, I mean, we've said this word bijection, but we really haven't talked about what this is saying. So what do we have now? We have the set of all subgroups of the Galois group of F. And we then have this one-to-one correspondence between the set of subgroups and the set of fields that lie in between, I erased that, but lie in between K and sigma. So there's this correspondence, that's the Galois correspondence, between subgroups of the Galois group and intermediate subfields of the extension. And so what this gives us, and so let's say it like this, so interpretation of A is that, so every intermediate subfield M in between K and sigma is the fixed field of some subgroup of gamma of F. What is that saying, or how do you, or why am I able to say this? Because since we know it's a bijection, we know it's onto, so every intermediate subfield, every element of F star is equal to phi of G for some little, or some capital G in script G star. Okay, so that's really just saying that our mapping phi is onto, and so continuing this sentence here, so and every subgroup G, so every subgroup of the Galois group arises, oh wait, how do you spell arises? One more. Arises as gamma sigma m, which equals gamma m for some m in script F. Now, okay, so there's this one-to-one correspondence between subgroups and fixed fields. And how this correspondence works, so now we need to remember, since, phi and gamma are inclusion reversing, this gives a I don't know. Well, I don't know how to say this. It gives an isomorphism between the certain lattices. But let's say it this way. Let me rephrase this. We can build the inverted. Let's say it like this. The inverted subfield lattice for the extension sigma over k from the subgroup lattice of gamma of f, and vice versa. So let's say and vice versa. Okay, so what is that saying then? If you've drawn the subgroup lattice for gamma of f, then you will be able to draw, exactly what the subfield lattice for sigma over k will look like, right? If you look at all the subfields that live in between sigma and k, or k and sigma, it forms a lattice, and it will look like an upside down version of this one right here. That's where that inverted word comes from. You'll see what I mean once I actually do a computation. So let's just get into it now. But the whole idea is that there is this backwards and forwards correspondence between subgroups and subfields, right? And it actually gives us some nice pictures once we're in it. Okay, so as our first example, let's compute the Galois group, and I'm going to put a little sub q here. This is equal to the Galois group. I need to specify the coefficient field. So it's the Galois group gamma of sigma over q, where sigma is the splitting field for the polynomial f equal to, and we're going to do x to the fourth minus 5x squared plus 6 right, over q. Okay, so we want to compute the Galois group, and then from that, what we want to do once we've done that, so let's sketch the subgroup lattice for gamma of f and the corresponding inverted subfield lattice for sigma over q. Okay, so the first thing we need to do is figure out who our sigma is, who the splitting field is. So let's see, x to the fourth minus 5x squared plus 6, that's going to be an x squared minus 3x squared minus 2. And so the roots, say the set capital R, that's going to be plus or minus root 2 and plus or minus root 3, which means that sigma is going to be Q adjoin root 2 and root 3. We've looked at this one before. In fact, we already computed gamma of f in a previous example. So we computed gamma of f, which is gamma of q adjoin root 2 root 3 over q. Sorry, I'm out of room. That was just ought q adjoin root 2 root 3. And we saw, right, that it had order 4, and it turned out to be isomorphic to z2 plus z2. So it's isomorphic. Well, okay, so it's equal to, as a set, I called them 1, sigma, tau, and sigma tau. But isomorphic to z2 sum z2, where sigma interchanged plus and minus root 2, and tau interchanged plus and minus root 3. So this would be where sigma takes root 2 to minus root 2 and leaves root 3 alone. Oh, root 2. And tau leaves root 2 alone and interchanges plus and minus root 3. Okay, so we already described this group right here. And then the fixed field, so there's phi of the identity. Well, everybody's fixed by the identity mapping, so that's q adjoin root 2 root 3. And then we saw that the fixed field of the subgroup generated by sigma, that was q adjoin root 3. The fixed field of tau is q adjoin root 2, and then, oops, I still need the fixed field of the subgroup generated by sigma tau, that's equal to q adjoin root 6. So we computed all of this a little while ago. Okay, so now let's draw the pictures. Now, here's the problem. I mean, typically when you draw a subgroup lattice, you draw the big group at the top, you put the identity at the bottom, and then you do the in-between stuff. Now, here's what happens when you draw the fixed field lattice and compare it. One of them is going to be flipped over, meaning that so let me just do this. I'm going to draw the subgroup lattice upside down so that the fixed field lattice is right side up. Okay, so the subgroup lattice in upside down form looks like this, and then we've got, so let's put sigma here, tau here, and sigma tau here. I think when you're doing field theory, it's traditional to put the subgroup lattice upside down so that the field lattice is actually right side up. Okay, so here's how this works then. Corresponding to 1, we have the fixed field, right? Corresponding to the trivial subgroup, we have the fixed field q adjoin root 2 root 3. Okay, corresponding to the subgroup generated by sigma is the fixed field, and so right over here then, I will put q adjoin root 3. Corresponding to the subgroup generated by tau, we have q adjoin root 2. And then over here we'll have Q adjoin root 6. And then finally, at the bottom, we will have Q. Oh, which, by the way, I guess I should have written down, right? Phi of gamma of F is equal to Q. Right? Okay, so here's what I mean by the inverted thing. Because of the inclusion reversing process, we have that one of them is going to be upside down. And typically we'll draw the group one upside down so that the field one is right side up. Oh, I just noticed I left my zoom on. Hold on. Okay, so there's our first example, and let's see what time we got here. Yeah, let's do one more example. Okay, so for our next example, we are going to do, let's compute the Galois group of the polynomial f with coefficients in Q. So this is going to equal, right, gamma of sigma over Q, where f is equal to x cubed minus 2. And then I want to sketch the corresponding lattices. So we'll say in sketch the lattices. All right. Okay, so let's write down the roots first. And here's one way if you want to do it the complex analysis style. So let's let omega equal e to the 2 pi I over 3. All right, so there is our primitive third root of unity. All right, and then, so if we were looking at the polynomial x cubed minus 1, then one of the roots would be this one right here. The other ones would be the powers, right? So this thing squared, this thing cubed, which would be 1, right? Those would be the roots. So if we take the primitive root of unity and scale it by a factor of cube root of 2, right, then we get all the roots. So, yeah, let me write this out. So this is cosine of 2 pi over 3 plus I sine 2 pi over 3. This comes out to be negative 1/2 plus I square root of 2. So then our set of roots is going to be two to the 1/3, 2 to the 1/3 omega, and 2 to the 1/3 omega squared. Now, and hold on, I gotta fix one thing in my notes here. Now, one thing we know is that the Galois group of the polynomial is going to be a subgroup of the permutation group of the roots. So by, this was by 5.6, gamma of f is a subgroup of the symmetric group on the set of roots, which we know is isomorphic to S sub 3, right? So we can think of gamma of f as a subgroup of S3. And in this case, we know that f is an irreducible, so this polynomial by Eisenstein or whatever you like, this is irreducible over Q. So since f is irreducible over Q, we know that gamma of f acts transitively on capital R. Right, so there will be, given any two elements in here, there will be a permutation, an element of gamma of f that takes one to the other. Now, okay, so let's write down, so sigma is equal to, well, okay, so I mean, how would you get it? You get it by adjoining all the roots, right? So it's Q adjoin all the roots. So it's equal to Q adjoin, and one way to do it would be to say it's omega and 2 to the 1/3, but let's see, how did I write it? Oh yeah, so it's equal to Q adjoin, so let's see, if we look at omega, it's 1/2 plus I root 3 over 2, so really all we need to do is get the I root 3 in there. So it's equal to I root 3 combined with 2 to the 1/3. Now, since sigma over Q is Galois, we know that the order of the Galois group is equal to the degree of the extension, which is going to be equal to, I'm going to Tower law this now, so this is sigma over, let's see which order I want to do this in, sigma over Q adjoin 2 to the 1/3, and then we'll have Q adjoin 2 to the 1/3 over Q. Obviously, for this one, we've got the minimal polynomial, so this is a degree 3 right here. And now what did we do? Well, we adjoined I root 3, which will have minimal polynomial x squared plus 3. Right? And so you can check that the minimal polynomial is x squared plus 3, the minimal polynomial over 2 to the 1/3, or Q adjoined 2 to the 1/3. And so in the end, what we have is that the order of gamma of f is equal to 6. Okay, fine. But what did we know? We know that gamma of f is a subgroup of S3. S3 has order 6, and so if you're a subgroup that has order 6 within a group of order 6, you've got to be equal. So our conclusion is that gamma of f is isomorphic to S3. Okay, now we would like to get a better feeling. We really want to understand how the how this group, what does this group look like? What do the elements look like? And so one way to get a feeling for how a group, what the elements look like, is to identify the generators for the group. So what we want to do is find a generating set. So, and that will be typically what we do once we have an idea, okay, here's the size of our group, we'd like to identify who it was. In this case, it was easy because we had this order 6 business. But in general, what you want to do is identify the generators for the group, right? Just like we did before, we had sigma, tau, and sigma, and then the other non-trivial element was described as sigma times tau. So, to find the generators of gamma of f, here's what we do. So let me just write these things down. So first of all, sigma over q has basis. So what do? We take the bases for these two extensions and we mix and match, and so there's going to be 6 basis elements. 1, 2 to the 1/3, 2 to the 2/3, and then we multiply these by omega. So omega times 2 to the 1/3, and omega times 2 to the 2/3. So now that tells us then that if we want to know what an element of gamma of f looks like, well, it's going to be completely determined by knowing what it does to 2 to the 1/3 and omega. We can say, so any element of gamma of f is determined by the images of 2 to the 1/3 and omega. The next thing, of course, any element, let me leave that up there, in fact, any element of gamma of f permutes the roots of r. So, or any element of gamma of f permutes r. In other words, okay, if you want to know what's happening, take some element in gamma of f, you need to understand what it does here, but then it also has to behave as permutation. So it tells us sort of the targets for these things right here. Last thing, okay, so that was bullet point 1 here, that's bullet point 2, and then bullet point 3, think about S3. S3 is generated by a rotation and a transposition. Okay, so those three ideas or those three facts are going to allow us to figure out who the generators of the group are. So what I want then is an automorphism of sigma that fixes Q, of course. I want one of them to be a rotation, one of them to be a transposition, an order 2 element. So, and so let me just draw this little picture here. All right, I want to put our roots. All right, we've got 3 roots. They lie on an equilateral triangle sitting inside the complex plane. So here's 2 to the 1/3. Here's 2 to the 1/3. 2 to the 1/3 omega, and here's 2 to the 1/3 omega squared. Okay, so now this picture kind of helps us, right? You can imagine one of the elements, the rotation, is going to be a counterclockwise rotation. So sigma, let's say, how do I want to write this? It takes 2 to the 1/3 to 2 to the 1/3 omega, and it takes what does it do to omega? It takes omega to omega. Yeah. And then tau, it's going to, what does it do? It leaves 2 to the 1/3 fixed, and it takes omega to omega squared. So 2 to the 1/3 goes to 2 to the 1/3. No, and omega goes to omega squared. So what's happening here, you can see, so 2 to the 1/3 goes to 2 to the 1/3 omega. That's this part right here. And then you need to figure out what happens with omega in that case. And then the flip, right, you can think of interchanging these two roots right here. So what would that do? It would take 2 to the 1/3 to 2 to the 1/3, and then it would take omega to omega squared, right? That's our transposition. So now, gamma of F is equal to the subgroup generated by sigma and tau. There are 5 proper subgroups, so gamma of F has 5 proper subgroups, and I computed these out. So they are, but here they are in terms of order. So there's one of order 3, order. 3 of order 2, and 1 of order 1, right, the trivial subgroup. And here they are, so written out in terms of the generators, so they are the trivial subgroup. This one has order 3, right, because sigma is our rotation. Then we've got 3 of them of order, that should say 3 of order, 3 of order 2, right? So that'll be sigma. No, it will not be. It will be tau. It will be tau sigma and sigma tau. All right, so those are our proper subgroups. Now, okay, so next we need to identify the fixed fields. And I'll let you actually do the cranking of these. I worked these out. So it goes like this. Obviously, the fixed field of the identity fixes everybody. So this is going to be, sigma, which is Q adjoin. How do we write this? 2 to the 1/3 and omega. Is that what I have? Yeah, omega. The fixed field. So we've seen how to compute these already. If you want to compute the fixed field of sigma, right, it turns out to be Q adjoin omega. And let me just remind you how you compute this, right? So you need to be fixed by every element of the subgroup generated by sigma. And so what you do, okay, you say, okay, what happens if we do sigma of A plus, who's our basis? B, how do I write the basis out? Sorry. 2 to the 1/3, B times 2 to the 1/3, plus C times 2 to the 2/3, plus D times omega, plus E times omega 2 to the 1/3, plus F times omega times 2 to the 1/3. Okay, so if you compute this based on the formula, you're going to say, okay, whatever we get here, I need to be equal to this. So you figure out who the A, B's, and C's and so on are going to be. And what it'll turn out to be, right, is it will require what? The A, B, C, E, and F are equal to 0, I guess. And so it'll be just the subfield generated by omega or Q adjoin omega. Okay, so do those. So I want you to compute those out. Where did I go? Let me write the rest of them. The fixed field of the subgroup. Oh, and by the way, it also has to be fixed by sigma squared, right? So you need to do sigma, figure out what the A, B's, and C's need to be for it to be fixed by sigma and sigma squared, and that will allow you to see that it's Q adjoin omega. The next one for tau is going to be Q adjoin 2 to the 1/3. Fixed field of, what else we got here? Tau sigma, subgroup generated by tau sigma, equals Q adjoin omega times 2 to the 1/3. The fixed field of sigma tau is omega squared. So Q adjoin omega squared 2 to the 1/3. And then finally, the fixed field of gamma of F, that's just going to be Q. Okay, so now for the lattices, well, let me put them, I guess I'm going to have to erase this, sorry, so I assume you've taken notes, you have this written down, but I'm going to erase this part. And so as before, I want to draw the subgroup lattice upside down. So I'm going to put the trivial subgroup at the top, and then we have sigma tau, tau sigma, and sigma tau. So here's the subgroup lattice for gamma F. And then next to that, right, we're going to have, so at the top is going to be sigma, which was Q adjoin 2 to the 1/3 and omega. Okay, the fixed field of sigma was, I think it was Q adjoin omega, and then we have tau's was 2 to the 1/3, right? Sigma tau sigma was Q adjoin omega 2 to the 1/3, and then the last one over here, Q adjoin omega squared 2 to the 1/3. Sorry, it's a little bit sloppy there. Hopefully you can see that. It's omega squared 2 to the 1/3. And then at the bottom, we have Q. Oh, now one thing to point out, in the last example I did, right, the Galois group was Z2 plus Z2. That's an abelian group, which means all subgroups are normal, which means that all the corresponding extensions were normal. In S3, right, there's only one normal subgroup, right? That's the one of order 3, right, the index 2 subgroup, which means this is the only normal subgroup, which means, right, that the only normal intermediate extension is this one right there. So we can say it like this. So since the subgroup generated by sigma is the only normal subgroup of gamma of F, we have Q adjoin, right? So this is the only normal one, so that's the only normal extension. So Q adjoin omega over Q is the only normal, or let's say intermediate normal extension. All right, so there's using part B of the fundamental theorem. And then the last one, or the last part, part C, is what? We also know that the Galois group of phi of W over Q then is isomorphic to gamma of F mod ideal generated by, or not ideal, but by subgroup generated by sigma, right? And this then is going to be isomorphic to Z2. Okay, so that's a good place to stop. We're going to do a couple, or quite, actually, let me just see how many more examples I have here. One, that's a giant example. Two, oh, I guess just two. I'm going to do two more examples, including one that's a pretty lengthy example. Okay, so we'll do one more lecture's worth of examples of splitting fields, and then we're going to move into the next phase of Galois theory, right? So we've done the fundamental theorem, but remember, we're still supposed to be talking about what it means to, or why there is no formula for extracting roots of polynomials of degree 5 or higher. So we'll need to say exactly what we mean by no formula. That'll be one of the first things we do. And anyways, okay, so enough for now. All right, see you later.